saying that, okay, so everyone got a copy of the practice test, right? I know it's short notice to have this completed by Wednesday. Remember, it's just completion marks anyways. So as long as you've done like 2 out of the 5 questions, I'll give you the completion mark. How about that? So it's definitely worth putting some time into. Remember, it's worth the same as assignment 5. Assignment 5 is really long, right? But this one's a guaranteed 100%er. So if you do some work, right, at least 2 of the 5 questions, then you get the completion mark. Okay, so I'll write that down. Because it is for Wednesday, and I know that's short notice. Our test isn't until Monday, right? But we'll do the review on Wednesday, and so we'll go through this together on Wednesday. Pardon? The 18th. Yeah. All right. So let's see here. Scroll down, down, down. Oh, yeah, yeah. We've done a lot of this. Oh, that's right. We were going to do Jocko's Garage. So I'm going to say here, this is for March 11th. Test number 2 is on Monday, March 18th. Do at least 2 of the 5 problems on the practice test before class on Wednesday, and that's March 13th, just so we're keeping these dates straight, for 1 completion mark. We will go through the practice test. The practice test together on Wednesday. Test 2, notice how long this is, really long, okay. Test 2 is gonna have the same number of questions, okay. Thing is, question 1 is fixed, it has to be there, it's from chapter 4, so it's gonna be on there, okay. And then what's gonna happen is I'm gonna give you all of these, so 2, 3, 4, and 5, but you only pick 2 of them to do, and then you just tell me the type that the other 2 are that you're not doing. Okay, so you only have to do 2 of the 4 later ones. Okay. So for test number 2, question 1, in reference to practice test. Question 1 has to be there, and then pick 2 of question 2 to question 5 to do completely. Tell me the type of the other 2. This means that you have to read all these questions and decide what type they are, right? We've got one sample mean sigma known, one sample mean sigma unknown, matched pairs, or two independent samples, which we'll talk about today, right? But when you're reading these questions, right, you're gonna try to figure out what type they all are. And then if you have a favorite type that you like to solve and like to work with, then just do that. Notice on the practice test, right, it's just do a hypothesis test, do a confidence interval, do a hypothesis test, do a confidence interval. So that's what you can expect, right, for all of these questions. So it's gonna feel a lot longer than it actually is, right? And yeah, so you have to tell me which ones you're doing, tell me the type for the other two for 1 mark each, and then you're A-okay. So if that doesn't make sense, because I know that's kind of a weird setup, but it's because I want to give you the chance to do the ones that you like, right? Or the ones that you know you've got under control, right? And then, and I'm also really curious to know which ones you pick. Yeah. No. No, I won't do any bonus. So you have to tell me, so you have to commit to which ones I'm marking, right? Otherwise, it's a lot of marking for me. Fair, but no. Okay. Yeah.
Change the question one at all. It's gonna be verbatim for the test.
What do you mean? No, the question one type. Yeah. No. Verbatim. No, what's the point in that? But it's going to be the same type, just because it's a little bit different, right? It's using the Z-scores to find probabilities and that kind of fun stuff. Okay. All right. Any questions? Okay. So we're going to kind of zip through Jocko's Garage, because we kind of talked about it, I think, last day. Or no, I remember. I told you guys to go home and work on it on your own and see how that worked out. And I know that's exactly what you did. Wednesday afternoon, you said, I can't wait to get home to work on this. So we're just going to do a Coles Notes version, just because we don't have a lot of time. And we already went through an example of it. Not together, but. So the question was, insurance adjusters are concerned about the high estimates they're receiving from Jocko's Garage. Oh, side note, test 2 is really only on chapter 4 and chapter 5. Assignment 4, assignment 5. They're concerned about the high estimates they're receiving from Jocko's Garage. And so to see if the estimates are unreasonably high, they have 10 damaged cars. They all have different amounts of damage, right? So little bit of damage wouldn't yield that high of an estimate at either garage, right? And so each of the cars goes to Jocko's Garage, and then it goes to the trusted garage. And we've got the estimates for each car, right? Because we're looking at, well, here's car 1, and we've got 2 measurements on the same car. That's what makes us say that this is paired data or matched pairs. Remember, I use those interchangeably. Okay. So here, part A is this paired data. Yes. Since we have two estimates, from each car. If you just came in, make sure you grab the practice test after class, because that's for next day. So is this paired data? Part B is kind of fake, because then later in D I give you the information, right? But what we would do, remember the trick that we use for matched pairs is we calculate a new column of the differences, and then we calculate the mean and the standard deviation of the differences. And then we use those to analyze, well, is there a difference between these estimates, right, from car to car? So, wait. I'm just gonna skip in the interest of time. You'll see why I'm only because I have the information for you in part D. So let's do C. I'll add it to the bottom of these notes here. I'll call it Jocko's garage. I think it's such a funny question because you get to say Jocko's a lot. Jocko's garage. And he sounds suspicious. So part C was to set up the null and alternative hypotheses. I'm going to pull up the question so I have it. Oh, there it is. So your null hypothesis, remember what's nice about matched pairs is there's no value that you have to find in the question. The null hypothesis for matched pairs is always the same. It's always going to be, the null hypothesis is that mu d equals 0. Or on your formula sheet, I have mu diff, but d is just shorter than diff. And it's important that you have the mu subscript d just to emphasize that you know that you're analyzing the differences, right? That column of the differences. Where it gets tricky, especially for one-sided tests for matched pairs, is, okay, well, same rule applies that whatever you have your mu in the null hypothesis has to be the same value in the alternative, as well as you always have to talk about how it relates to 0. Right? The only difference is going to be that the sign in the alternative hypothesis. Here, we have to think about, okay, well, what would it mean in terms of the difference, how it relates to 0, if Jocko's estimates are higher than the trusted garage? Right? And so, if Jocko's estimates are higher than the trusted garage, and D was Jocko's minus the trusted, right? That's how I said we would calculate our differences, which we didn't actually go through and do, but you could go back and do it. So you calculate Jocko's minus the trusted garage for each of these values, and you find the difference. Well, if J is consistently higher than T, right, you're going to get a positive value for D. Then D is greater than 0, right? Positive. Another way that you could check that is just go back here and say, okay, well, 500 minus 430, 500 minus 430 is positive, right? And in this instance, right, 500 is higher than 430, and that's positive. And so that's how you know that if Jocko's estimates are higher, then you have a difference that's greater than 0, right? So a little bit tricky, right, to figure out what the sign is for the alternative hypothesis if you have a one-sided test for matched pairs. But here, so mu d must be greater than 0. This is making this a one-sided test, right? Because we only care about one extreme. Usually. There's, yeah, usually, yes. There's like rare instances where it's not, but. So, that's part C. So part D, I'll just add another page here. D, find the test statistic. Hard to say, fun to do. No, not really. We're just calculating the T, right? So T for matched pairs is x bar of the differences, and maybe I'll just use the one on your formula sheet. It's going to show you the technical one, but we did it last day, so minus 0 over the standard deviation of the differences over the number of differences. In part D, I told you that the mean of the differences is 80, and I'll go back and I'll put this into the table here. The mean of the differences is 80, and the standard deviation, if you calculate it, is 84.59052. So once you've calculated all these differences, if you then went ahead and calculated the mean and the standard deviation, that's what you would find. Okay, but I'm just giving it to you. So the mean of the differences is 80. How far is that from 0? Taking into account the standard deviation, which is 84.59052, divided by the square root of the number of differences, which is still going to be 10 because we've got 10 cars, right? So we've got 84.59052 divided by the square root of 10. I get 80 divided by 26.7498717. Could be off because I had a little slip here. But I get a T of 2.99, oops, I say 9, but right 2. 2.990668609. T, we always have to round to 3 decimal places, or at least 3 decimal places, right? So we get 2.991 to 3 decimal places. So these parts are just walking you through the different steps, right? So now part E, find the p-value. Find the p-value. We use the same setup all the time, right? When we've calculated a t and we use the t-table, first we outline what our degrees of freedom are, and then where our t is on the table, and then what that means in terms of our p-value. And so using the t-table, with degrees of freedom equal to nd minus 1, which is 10 minus 1, which is 9, we find, and before I even go to the table, I can set up this empty shell that I can fill in the values for, right? So in the center of the page, I'm going to put the absolute value of t equal to 2.991 is between 2 values. And then I'll throw a so in there. So remember, we have a one-sided test, so we need a one-sided p-value. So the one-sided p-value is also between 2 values. So this shell is always going to be the same, right? You're going to calculate your degrees of freedom for that problem, right? But it's always going to be the same using the t-table with this many degrees of freedom. We find your calculated t goes in here is between 2 values, kind of leaving room for those. So the one-sided or the two-sided p-value, depending on the question, is between these 2 values. So always using the same setup, because that'll make it easier to not miss anything. Okay? So now we can go to our tables, and we've got 9 degrees of freedom. Let's see if I can get everything on the same page here. Right, so we take our 2.991 that we've calculated, and we just try to place it somewhere along the 9 degrees of freedom line, and it ends up somewhere between 2.821 and 3.250. So what you would do is you would write those down, right? But just so, yeah, 2.821. Short-term memory is not that good. 2.821 and 3.250. So now I'll go back to the table to find where my one-sided P might be. So it's between here and here. So then I can roll down. So my one-sided p-value is somewhere between 0.005 and 0.01. Remember, the only switcheroo that you have to do is you have to read the p-values from right to left, because as you're moving further and further out into the tail, right, the area in the tail is getting smaller and smaller. So these are actually decreasing as your t's are increasing. So just keep that in mind. So our p-value is between 0.005 and 0.01. Wait. So 0.005 and 0.01. Now we know our p-value is somewhere in there. We can say it's really small. And so now we can go on to part F, which is our conclusion. So what can you conclude? Conclusion. Again, we use the same setup all the time, right? So since our one-sided p-value, is between 0.005 and 0.01. Did we get an alpha level? No. So the default, right, is 0.05. It is less than, right, because both of these values are less than 0.05. So it is less than our assumed alpha level of 0.05, which means we have enough evidence to reject H naught in favor of HA. So which means we have enough evidence to reject H naught in favor of HA. Which is kind of what we were suspecting, right? With a T of 2.991, that's really large, right? So we already suspected that we would be rejecting the null hypothesis. The p-value just confirms it. So therefore, Jocko's estimates are significantly higher because I ran out of room. And I call it there, but there's not much else you would say, right? You would just reword the question as an answer. The question was, is there evidence that Jocko's estimates are significantly higher than the estimates from the trusted garage? Yes, there is evidence that Jocko's estimates are significantly higher than the estimates from the trusted garage. But I shortened it. Any questions about that one? Okay. So matched pairs or paired data, I use interchangeably, of course. We can do confidence intervals, right? And so they look the same as for one sample mean sigma known. It's just that we're specifying that we're actually talking about the differences, right, still. And so this should look very familiar, right, for the confidence And what I'm going to do in the interest of time, because I do want to get through all of chapter 5 today, is I'm just going to let you read example 7 on your own, because the solutions are all typed up, and then we'll do example 8 together instead. And so if you have questions about example 7, you can ask me later. But for now, just because we have seen this before. All right. So example 8, confidence interval for paired data. That's what this is going to be. So a study tested whether wearing wetsuits influences swimming velocity. 12 competitive swimmers and triathletes swam 1,500 meters at max speed twice each, once wearing a wetsuit, a wetsuit. Interesting. A wetsuit and once wearing a regular bathing suit. The order of the trials was randomized, right? So they said, okay, you're going to do the wetsuit first, you're going to do the bathing suit first, right? So you don't all do it in the wetsuit when they're all nice and fresh, and then you put the bathing suit on. That just wouldn't give you good data, right? So the order of the trials was randomized. Each time, the max velocity in meters per second of the swimmer, and of course, among other quantities, was recorded. And here's a summary of the data. One telltale sign of you have a matched pairs or paired data type of question, is if I give you something like this, right? Because what we've got is we've got the wetsuit data, we've got the no wetsuit data, and then we've got the differences, right? Because each of the 12 swimmers did the wetsuit and then they did the bathing suit, right? And so we've got 2 measurements on the same subject, on the same swimmer. And so if I give you information like this, then I give you the mean of the differences and the standard deviation of the differences. Okay. So this is definitely a quick way to look at a question and just already suspect, if I give you the mean of the difference and the standard deviation of the difference, it's probably matched pairs. And so another way that I could do it is if you have a look and read through example 7, it's just in the question, right? So those are the 2 ways that I could give you the data. So I'm just introducing you to those 2 ways. Once you've decided that you have paired data, right, you can ignore the wetsuit, the no wetsuit information, because everything that you need is captured in the differences. Right? So I don't want to see you trying to incorporate these guys. Just look at the differences. So here, I'm going to say, okay, we've got paired data. Paired data analyzes the differences. So as far as identifying the type, we have 2 measurements on each swimmer. So we have paired data. And this is where it might be a good idea. I posted those assignment 5 extra problems with the solutions to those. And it's just a list of a bunch of questions that you can just read through and try to figure out which type of question is it. And then you can check the solutions just to make sure that you're on the right track, right? Because a lot of this is going to be able to, so reading a question, deciding what type of question it is, convincing yourself of that, and then just sticking to it. Because once you've decided what type of question it is, you know where on the formula sheet you'll be working, right? So you're not going to jump around anymore. So we want to make a 95% confidence interval for the difference in average max velocity for competitive swimmers and triathletes wearing wetsuits minus those not wearing wetsuits, blah, blah, blah. So we have our formula for our matched pairs confidence intervals. And so we've got X bar of the differences plus minus T star times the standard deviation of the differences over the square root of the number of the differences. X bar of the differences, so we know X bar of the differences from the table is 0.078. The standard deviation of the differences is 0.022. And the sample size of the differences is 12. That's just from the table. Just pulling out the information that we need. We need T star. Right, that's the only one that's missing. What we're going to do is we're going to find our degrees of freedom, and then we find our T star the same way that we did for one sample. This is just a special case of the one sample, right? Where our sample is about the differences. So using the T table, with degrees of freedom equal to ND minus 1, and this is it, the degrees of freedom are all on your formula sheet, right? So you don't have to memorize these or anything, which is 12 minus 1, which is 11. With a 95%, I think that's what we wanted, right? Yeah, confidence level. T star is going to be what? So we've got a 95% confidence level. So we've got that guy here. And then we're just going to go down to 11 degrees of freedom, 2.201, and that's our T star. So we've got a T star of 2.201. I'll add a page here. So again, now kind of for real, I'll write out my formula so I can fill it in. So X bar of the differences plus minus T star times S of the differences over the square root of the number of the differences. We had, what, 0.078 plus minus 2.201 times 0.022 divided by the square root of 12. 0.022 divided by square root of 12 makes 2.201 times 0.006350853 plus minus 0.078. To the next page, times 2.201. So my margin of error, which is that whole plus minus chunk, right, is 0.013978227. I'm going to store that. And then to write out my interval properly, right, I do round brackets, my lower bound, comma, upper bound. So first one is 0.078 minus the margin of error, which is 0.064021773, up to 0.078 plus the margin of error, 0.091978227. I don't know if is anyone else getting these same values or just trusting me? I only ask because, yeah, good. Because I do not remember this from this morning. So it's a wild card. So I always get suspicious when I start to not recognize numbers that I just did this morning. But I'm going to round these to, let's go with 3 decimal places, just because 2 is, we've got that 0 in front and it just doesn't look that good. Also, I gave you 3 decimal places, so let's just match those. So 0.064 up to 0.092. Once we've made a confidence interval, we interpret it, and we always use the same interpretation, right? We're some percentage confident that this interval, so the interval between here and here, captures, and then whatever I asked you to make an interval of. Right? Sometimes that's easier than others, as you'll notice on the assignment, but I'm sure you can come up with something. We are 95% confident the interval from 0.064 to 0.092 captures the mean difference in max speeds with a wetsuit versus not. Well, I guess I should say versus bathing suit. I'll add a little note here, right? Because for matched pairs, we're always talking about the differences. And so if a 0 was in here in this interval, then we would be able to say that no, there's no difference between these 2 groups, right? Because if it goes from a negative to a positive, then 0 is somewhere in there and 0 is likely to happen. Now we're saying no, we're actually 95% confident that 0 won't happen. In fact, it'll all be above 0. So then we could use that to reject the null hypothesis if we had to use the confidence interval to do a hypothesis test. I'll just say a little note here. Note. Since H naught is that mu D equals 0 for paired data, and our interval is consistently above 0, we could use our interval to reject H naught and conclude there is a significant difference in speeds. I'll just end it there. There is a significant difference in speeds with a wetsuit versus not, or with a bathing suit. So you can use that confidence interval to draw conclusions about a hypothesis as well. Any questions about that one? No. So we're gonna keep going into 5.3. And the reason I'm so desperate, or sorry, two independent sample means. The reason I'm kind of desperate to get through the last section of chapter 5 is because I want you to have seen as much as you can on a test before the final, right? Because all of this is going to be on the final, but at least if you've seen it in a test situation before, then it'll feel a lot better, right? Because then we only have chapter 6 and chapter 7 that'll be new for the final exam, right? So that's why I'm kind of like, we can do it, and we can, and we will. Okay. So matched pairs that we just talked about are kind of a special case where we have two samples, but we're able to match one observation here to one observation here, and there's some sort of natural pairing going on. Right? Often, the most basic case is that we just have two samples and we want to compare these two groups, right? You want to compare firm A to firm B, right? Salesperson A to salesperson B. You want to compare UBCO to Okanagan College. You want to compare males to females, right? So you've got these two independent groups where there's no natural pairing that says, oh, this student at Okanagan College has to get matched with this student at UBCO, right? And you don't need that. You just treat them as two independent samples. Okay? Now that you have these two groups, there's no tricks around it, right? We can't calculate the differences because there's no way to say that, oh, this is how we would find the differences, right? And so what we're left with is we just have these, imagine your spreadsheet, just these two columns of data, right? Each of which has a mean, each of which has a standard deviation and a sample size. Right? What's kind of cool is we can handle them not having the same sample size. So you could collect 17 females and 21 males, and you could still compare their averages. Right? And so you don't even have to have the same sample size for two independent samples to work. And so that's kind of nice. And the only kind of thing that we need to be aware of, right, is that now we have essentially twice as much information, right? We have two means, we have two standard deviations, and we have two sample sizes that we need to keep track of. One note here is that for matched pairs or paired data, we're analyzing the mean difference, right? The average of the differences. When we're looking at two sample means, we're analyzing the difference in the two means, right? Mean 1 minus mean 2 is what that's saying, right? And so the wording is, although it's really kind of minute, it changes everything, right? You've got mean 1 minus mean 2, whereas here you've got the mean of the differences. So what we're gonna have is we're gonna have some group 1 information, right? And we just use little subscripts X bar 1, S1, N1. And then group 2 information, X bar 2, S2, N2, right, to denote which one's which. And you have to define which one you're gonna let be group 1 and which one you're gonna let be group 2, because as long as you're consistent, it doesn't matter which one you assign to which, right? It does matter in your null and alternative hypothesis. I want to highlight this part. So here in the general case, I've got mu1 equals mu2. So again, what's nice is, so we said in matched pairs, we know what the null hypothesis is. So from there, we can kind of figure out what the alternative is. Same thing here for two independent samples. This is what your null hypothesis is going to be, right? You're going to be saying mu1 is equal to mu2. The only difference is you have to put on question-specific subscripts. For example, if you're talking about the mean of females versus the mean of males, you would have mu f equals mu m. Right? And that's just for me reading your work. When I look and say, well, should F be greater than M, right, depending on the question. And then if you just use 1 and 2s for your calculations, that's fine. So I'll show you what I mean. But I do want to highlight that. So for full marks on a test, you must use question-specific subscripts. This is the null hypothesis I have on your formula sheet, right? We could rewrite this and say, well, that's the same as saying that mu1 minus mu2 is 0, right? If they're equal, the difference is 0. So if you wanted to, you could use this one. Like I said, I've used this one because I find it more concise, right? This equals this. This doesn't equal this. Right? But this one is accurate as well. So you're welcome to use it, but I won't. Any questions so far? Oh. All right, so our T grows a little bit bigger, but once we have our T, we know what to do with it, right? We have to find our degrees of freedom, and then we can use the T table to find our p-value. Oh man, you're keeping up. Right, but once we have a T, we're in the clear. Then it's back to the same old stuff that we have been doing for all of chapter 5. So here we've got the mean of group 1 minus the mean of group 2. And then on your formula sheet, you'll notice that this isn't even here, mu1 minus mu2. Because remember, the null hypothesis, we always assume the null hypothesis is true. And the null hypothesis, we said we could say is mu1 minus mu2 is 0. So this will always just be 0, right? So on your formula sheet, pretty sure you've got, yeah. You just have this one here, x1 bar minus x2 bar over the square root of s1 squared, so only s1 is squared, over n1, plus s2 squared over n2. Remember, we have to keep track of 2 standard deviations, 2 sample sizes and 2 sample means, right? And so they all have to go into the T calculation. But once you've calculated this, then what this is telling you is how far is this difference from a difference of 0, right? Taking into account the spread. Once you have your T, you have to find your degrees of freedom, so you can use the T table. I have it on here because technically this is what the degrees of freedom are. That's nasty, right? We're not going to do that. But if you're doing something in R and it gives you some weird degrees of freedom, this is where it's coming from, right? Because it can just go through and do it, right? For us, and what's on your formula sheet, you've got this one, right? The degrees of freedom is the minimum function, so the minimum of n1 minus 1 or n2 minus 1. So the result of this function is just going to be the smallest of the 2, the minimum. Okay. What we're doing, right, is we're just taking the smallest sample size minus 1. And then we can draw our conclusion the same way. Once we have our p-value, right, then everything stays the same. How we draw our conclusion stays the same. So, whoops. We'll kind of breeze through this question because this one's all typed up, and then we'll do one together. You'll see that it's all the same. Any questions though before we do? So weights of diamonds are measured in carats. So the difference between the size of a 0.99 carat diamond and a 1 carat diamond, you can't tell the difference if you're just looking at these things. Yeah? And so, but we want to know if there's a difference in price for a 0.99 carat diamond versus a 1 carat diamond. So in order to do these calculations, what they did was they said, okay, well, 1 carat is going to be worth 100 points, 0.99 carat is going to be worth 99 points. And then we're just going to calculate the average point prices of these diamonds. And so what we've got is, we've got this table, and again, kind of dead giveaway of just 2 independent samples problem. And for that reason, if I was writing the test on Monday, I would probably go for the matched pairs, and I would probably go for the 2 independent samples, just because they're the easiest to know that that's the type of question that you have. Remember, for one sample means you had to figure out what value you're comparing the sample mean to, and that gets a little tricky. So for me personally, I would go for these last 2, but again, and because the null hypothesis is already determined for you, right? So that's what I would do, but again, your choice. I'm just curious to know what we choose. So we've got a mean for the 1 carat, a mean for the 0.99 carats, standard deviation. We had 31 carat diamonds and 23.99 carat diamonds. Notice that we're able to handle these 2 different sample sizes. A lot of the time, those studies still use the same sample sizes just because it's easy, right? You collect 50 males, 50 females, right? Even though those are independent samples, you still, I don't know, for some reason we like to have the same sample sizes, right? But we're able to handle it if we don't. Yeah. Is there evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds? So what I'm going to do is use question-specific subscripts in my hypotheses. And then as long as I've said which one's group 1 and which one's group 2, I can just use the formula from the formula sheet in my calculations, right? Because doing 1 and 0.99 gets a little tedious down here. You're welcome to, but you don't have to, right? So as long as you've determined or told me which one's group 1 and which one's group 2, then that's fine. And here you're just doing the question-specific ones to help me out when I'm marking. So our null hypothesis is that they're the same. So these mean point prices are the same for each of these 2 groups until we have proof otherwise. And so, and what we're hoping to show, just like the question's asking, right, is that mu1, is it greater than mu 0.99? So we've got a one-sided test here. Oh, I've got that written down already. Do a little arrow. Here. Woo. If we do the test, right, so now we're ready to do our calculation. And although it's a little bit more work, right, we've got this huge square root that we have to deal with. Don't forget to square these values. And then finally, don't forget to take the square root in the end, kind of a common mishap. As long as you show your work, then if you look ahead to the confidence interval, as always, it uses the same thing that's in the denominator of your t as the margin of error, right? So you've got, in your confidence interval, you've got the same value. So what I'm trying to say here is, because on the test it's going to be part A, do a hypothesis test, part B, do a confidence interval. If you've shown the work once, and you've shown that this equals this, you only have to do that once, right? So in part B, you would say, this equals this from part A, right? And I'll show you what I mean by that. Just saves you a lot of time, right? You don't have to recalculate it. Don't worry, if for some reason something went wrong and you've got the wrong value here, how are you supposed to know that? So I just follow through and make sure that what you did was good, right? The thought was good. So if you told me that that's what it equals, then that's what it equals. We have our T, 2.507 already. we suspect that we're going to be rejecting the null hypothesis, right? Because we've got a quite a large t, right? Bigger than 2. But we can find the p-value just to make sure. So using the t-table and this is how you're going to write it out. So with degrees of freedom equal to the minimum of n1 minus 1 and n2 minus 1, that's just from your formula sheet. And then you're going to plug in your n1 and n2. So you're finding the minimum of 29 or 22. The minimum of 29 or 22 is 22. So that's your degrees of freedom. Good. I know that's a little bit, I don't know if you've worked with minimum functions before, but I think once you have a look, it's pretty straightforward. Again, we start and we write out our absolute value of t is between, if we went to the t-table, we could find it's between 2.183 and 2.508, which means our one-sided p-value is between 0.01 and 0.02. And that's just using our t-table the same way that we have been doing. Since our one-sided p-value is between 0.01 and 0.02, it's less than our assumed alpha level of 0.05, which means we have enough evidence to reject H naught in favor of HA. In this case, this means that there is a difference, or there is evidence that the average point price of 1 carat diamonds is significantly higher than 0.99 carat diamonds. What does that mean? Well, it's up to you, right? But if I'm telling you that you can't see the difference when you're looking at the two, but one is significantly cheaper than the other, I think we all know what to do. Okay. Any questions about that one? So same thing over and over and over again. We'll go through this example that I thought was kind of risque until I got to the end of the question. I was like, oh, okay. But I stole it anyways. A study examined the impact of the color red on how attractive men perceive women to be. In the study, men were randomly divided into 2 groups and were asked to rate the attractiveness of women on a scale of 1 to 9, not attractive to extremely attractive. One group of men were shown pictures of women on a white background, and the other group were shown the same pictures of women on a red background. I'm thinking filters, people. No. The results are recorded below. So here on the red background, 15 men were assigned to that group, just randomly assigned, hey, welcome, you're in group 1, you're in group 2. They found a mean of 7.2 with a standard deviation of 0.6. And then the white background, a mean of 6.1 with a standard deviation of 0.4. Again, this information is nicely laid out in a table. It could be that the information is just in a blurb. So what I would recommend is just read those types of questions that I've given you, those example 5 practice questions, or assignment 5 practice, extra practice. I don't know what I called it, but there's solutions as well. And just have a read, because there are some in there where this information is just in the blurb. Right? So just get used to reading that as well. But usually I'll just arrange it like this. The data for both groups are reasonably symmetric with no outliers, blah, blah. That's just checking the assumptions, which we're not really doing for this section. We will do for chapter 6. Is there evidence that the men who saw women on the red background rated them as more attractive? Okay. So we're going to do a full hypothesis test. First, we're going to talk about, well, what type of question is this? Sometimes it's as simple as, well, we have 2 independent samples, and so we have 2 independent samples, right? I don't know how else to say this. 2 independent samples. As men were randomly assigned to two groups or to two different groups. You only have to tell me what type it is. You don't have to explain why. Okay, but I'm just doing it because to show you what I mean. But sometimes it looks a little silly like that. Like it's two samples because it's two samples. I don't know what else to say. Okay. All right. Step one is to state the hypotheses. H naught is that mu R equals mu W, right? Using those question-specific subscripts just to make it easier for me when I'm marking to see if the sign in your alternative hypothesis is correct. The alternative hypothesis, what we're trying to see is if the red background is higher than the white background. So mu R is greater than mu W, making this a one-sided test. Because we're only concerned with one extreme. Okay. Step two, I'm going to add a page here. Step two, we have to do the test. So we're going to calculate T is x1 bar minus x2 bar over the square root of s1 squared over n1 plus s2 squared over n2. On the side here, I'm going to let group 1 be red and group 2 be white. Got those those numbers here. We've got all this. As long as we keep track of which one's group 1 and which one's group 2, right, then we'll be okay. So we're just going to plug in these values. So x bar 1 is 7.2 minus 6.1 divided by the square root of 0.6 squared over 15 plus 0.4 squared over 12. So I'm going to be careful just the first time that I'm calculating this whole square root, just to show all my work so that I can go back and recycle it if I have to. So I've got 0.6 squared, and I'm just going to do these very piecewise so you can check your work if you're working along later at home. So first I'll do 7.2 minus 6.1 is 1.1 over the square root of 0.6 squared is 0.36 over 15 plus 0.4 squared is 0.16 over 12. 0.36 over 15. So I get 1.1 over the square root of 0.024 plus 0.16 divided by 12, 0.0133 repeating, plus 0.024. Remember keeping all your decimal places as you go along? So I get 1.1 divided by the square root of 0.03733 repeating. Here's where you don't want to forget that square root. Right, so take the square root of that little guy. So you get 1.1 divided by 0.19321837. I'm going to store that and make a note of it here. I've stored it in one. Make sure I did it. Oh. So now I can do 1.1 divided by that guy. It happened again. It's not 29. Did you guys follow along? Did you get the 0.19? Yeah. So for some reason it's not doing, yeah, 5.69. See, I was getting 29 something, which is possible. It's just, since I know I stole it from a textbook and they don't tend to do that. So 3040865. Good. So to 3 decimal places, we have 5.693. Oh no, I'm just making a note for you, yeah. But you have to have at least 3 decimal places. So now we have our t, it's huge, it's 5.693, right? So already we kind of know we're going to reject the null hypothesis, but we have to go ahead and find the p-value anyways. So step 3, find the p-value. I'm going to use the same setup that I have been doing, even though what we're going to find is that 5.693 is off the table, right? But just to show you how to handle that, in this case, I'm going to set up my empty shell. So using the t-table with degrees of freedom equal to, and this is just from your formula sheet, the minimum of n1 minus 1 or n2 minus 1, which is the minimum of, I guess, 30. Was it 30 minus 1? No, not even close. 15 minus 1 or 12 minus 1, which, if you wanted to skip to this one, is just the minimum of 14 or 11. The minimum of those two is 11. We find, again, I'm going to start by putting my calculated t and absolute value brackets in the center, right? So I'm going to start here, t, absolute value of t equals 5.693 is between 2 values. So, and we have a one-sided test, so our one-sided p-value is also between 2 values. If we go to our table with 11 degrees of freedom, I'll just show that. So we have 11 degrees of freedom. We're taking our 5.693 and we're trying to place it, and all of a sudden we ran out of table, right? And so all we know is that our 5 point whatever is larger than 4.437. And that's all we need to know. And so what we're going to do is we're going to write that in here. So 4.437 is on this side of 5.693. Now I forgot, was it 4.437? I'm not done. So here, t, remember, t goes from negative infinity to positive infinity, right? And so on the upper bound, if you wanted to, you could put infinity. Or if you want to, you can just drop it, right? So because I like to have two sides, I'm going to do both sides, right? And what I would do there is just infinity here. But what I'm going to say underneath here is that this little bit is optional. So if you don't like the look of that, then you can drop that part. Right? All you need to tell me is that 5.69 is bigger than 4.437. And then to find our p-value, right? So we're bigger than 4.437, which means our one-sided p-value, right? P-values are decreasing as we move out here, is smaller than 0.0005. So our one-sided p-value is smaller than 0.0005. Just because we do that switcheroo when we read the p-values. Again, this part is optional, but the p-values are between 0 and 1, right? Probabilities are between 0 and 1. And so the one-sided p-value is somewhere between 0, because if you've reached infinity, the area in the tail past infinity is 0. Right? So good luck getting there, but that's when you would have a probability of 0 being higher than it. And so technically, our one-sided p-value is somewhere between 0 and 0.0005. But again, this part is optional. So you don't have to have that on there, but you do have to have this part and this part. Any questions about that? On the assignment, you have a similar situation, except your t is on the left-hand side of the smallest value of t. Right? So then things are reversed a little bit. Right? Then your p-value is bigger than the largest p-value on the table. You'll know it when you see it. So all we know is that our one-sided p-value is really, really small. Right? So now for our step 4, for our conclusion, we can say, since our one-sided p-value is less than 0.0005, it is, and again, there's no alpha level that I've given you, so we use 0.05. It is less than our assumed alpha level of 0.05, which means we have enough evidence to reject H naught. We have enough evidence to reject H naught. And if you're rejecting it, may as well say in favor of what? In favor of HA. In terms of the question, therefore, there is evidence that the men, and I'm just rewording the question as an answer, right? There is evidence that the men who saw women on the red background rated them as more attractive. As more attractive. I know I'm out of time, but well, I'm not truly out of time. I can squeeze out a confidence interval. Let me show you. Construct a 98% confidence interval for the mean difference in ratings. For the difference in mean ratings, just to clarify. What I'm gonna do is, because if you have a look at the formula, it's on the next page. Right. We've got x1 bar minus x2 bar. But we know that this is 1.1 from the hypothesis test. Plus minus t star. That one we have to find, right? But times the square root of s1 squared over n1 plus s2 squared over n2. This whole chunk, you can just tell me that you know that that is, let me see here, recall 1.193218357 from the hypothesis test. And then all you have to do is find t star. Right. So I know I've used up my time. So what I'm going to do is I'm going to finish this example just on my own. And I'll post that with the notes, as well as the last example 12, right? But I just wanted to show you how you can recycle information. If you've shown the calculation properly once, you can recycle it definitely for your confidence interval, or vice versa if you want. Okay. Any questions? No? All right. See you later. If you're in my labs, you should probably come to lab this week because I'm giving you basically the answers. Yeah, ish. It's like sort of. What happened? How's the lab? Easy peasy.
Can I just get the
Oh yeah, you bet. There you go. Yeah, if you didn't get a practice test, then come and get it.
Jimmy from